Hello, my name is José CAPMANY and I work for the Universidad POLITÉCNICA de Valencia in Spain, and I am also a founder of Photonics. I'm very happy to have the chance of delivering today this short video tutorial on field programmable photonic gate arrays. The agenda of this talk is the following. I will provide an introduction to the subject, and in particular I will pay a little bit of emphasis on programmable photonics, because this is a part where the particular device which I'm going to talk about today is part of. And this device is the field programmable photonic gate array. And I will provide some of the principles of operations, as well as some of a description of the main blocks and of the applications. And I will then summarize and finalize the talk. So, as an introduction, this talk is about a particular device and also about an area where we want to make use of reusability. And reusability in information and communication systems is very important because it has been a key aspect in many of the past revolutions. And for example, I include here a picture of SpaceX rocket. SpaceX is actually trying to incorporate reusability into spatial industry. And this is because there are great savings expected if, for example, one rocket can be used for 1,000 times instead of once. And as a rough figure, 60 million total project cost used 1,000 times becomes a 3 orders of magnitude reduction in the space mission costs. On a different scale, in the size of systems, of course, but on other application areas, we found this concept of reusability in some information and communication parcels. For example, in electronics, we know the field programmable gate array devices are used instead of application-specific integrated circuits. In networks, we are now very familiar with the software-defined network paradigm, where we actually, instead of designing ad hoc networks, we provide a general infrastructure and we operate and allocate the resources as they are needed by means of software. In radio, for example, we have software radio receivers which replace specific hardware receivers. Okay, so going a little bit further, and as we are today, we have a problem is that we have a lot of applications that are arising and are emerging, and these applications require flexible, faster, and very power efficient hardware. And of course, this has been traditionally been supported by electronics, but there are signs that the Moore law, which was holding for many decades now, is starting to saturate. And of course, the need for more bandwidth, more processing capacity is not going to stop. And however, some of these applications that are emerging might need some non-traditional computing approaches. So mixing all together, we have this very wide range of applications, which include telecom, sensors, bio, transport, quantum computation, artificial intelligence. And it apparently seems that electronics will need at the given time to team up with other technologies to meet these requirements for more processing speed and more bandwidth. And of course, photonics is an ideal complement to electronics because it provides bandwidth, it's low power consumption, and of course it has complementary properties to electronics. And so far, there's been a lot of activity in integrated chips and integrated photonic chips, but most of them have been like it happened many years ago in electronics, application-specific driven. So these aspects, as we call them, are being successfully integrated into many applications, but they face some problems because the time to market and fabrication cost and fabrication cycles are not optimized, and sometimes they act as showstoppers, by the way. So one way to overcome this is try to do the same thing that was done in electronic like 30 years ago, that is to incorporate programmability into the optical chips. So it might be the time that the time for programmable photonics has come. So we wouldn't be surprised if we see the emergence of solutions, similar solutions like to DSP, FPGAs, microprocessors perhaps, being developed into photonics. So just to go back, by the end of the 60s in electronics, there was a transistor had been invented, of course, the integrated circuit. But by the end of the 60s, one of the inventors of the integrated circuits, Paul Noyce, also a founder of Intel, he noticed that there was a rapid proliferation of different integrated circuits, each one designed for a specific purpose. And he was worried about this, and he predicted that there would be a solution to this problem that would be based on the development of general purpose chips that could be manufactured in huge quantities and also adapted to specific customer needs by programming. Okay, so this is the genesis, let's say, of probably the microprocessor and many other devices. Interestingly, Intel was a company that developed the first microprocessors, but later on, there was another processing element, programmable, which has been also very successful, that is the field programmable gate array. That, as you see here, is an array of computing logic elements. Each of them is made of a set of irreversible electronic logic gates 2 by 1, and they work on digital signals, and they are based on Boolean algebra, and they have been extremely successful. And nowadays, FPGAs are used almost in any kind of application that you can imagine. So, why FPGAs have been so successful is because they have advantages that supersede the capabilities of application-specific circuits, and most notably the time to market, the fact that the so-called non-recurring engineering costs are low because they are shared by all the designs. So also the design flow is very expedite because it's very fast, and also because they are very flexible. And if you see a time evolution of electronics, you see that there was like a kind of 40 years lag before the first discrete elements were invented, the transistors, until the FPGA was proposed. And from then onwards, there's been an area where both ASICs and FPGA coexist. So let's try to define or to describe a little bit more about programmable photonics. Programmable photonics, what we want to do is build photonic integrated circuits for which we can change to a lower or higher degree its properties by acting over its elements. And in this case, we don't have transistors, but we have phase shifters. So the evolution has been very similar to integrated electronics, I should say, in a way. We started with a reconfigurable application-specific circuits where you have a specific topology, like, for example, it could be ring resonators or Mach-Zehnder interferometers, and you can change some of its properties, tuning the resonances, the characteristics by acting over the phase shifters or internal couplers. From these designs, we move on to few, what we call few functional aspects. These are a little bit more elaborated structures where they still have a fixed topology, but they can be used to emulate or to provide 2 or 3 non-optimized functionalities. From that, we evolved to multiple programmable interferometers, which are N by M input-output port structures, where by acting over internal couplers or phase shifter elements, we can actually program any kind of linear matrix transformation. And from that, we have evolved to what we call waveguide meshes. And the waveguide meshes is like 2D arrangements of these programmable basic unit elements, which are like tunable couplers or tunable Mach-Zehnder couplers and phase shifters, which are arranged in a specific spatial pattern, like in this case it's an hexagon, but it could be a triangle or squares. And basically these elements can emulate almost any kind of programmable circuits. And as you can see, they have not a prescribed topology. So it's like a tapestry, geometric 2D tapestry, and it is the ability to program these elements that allow you to configure or emulate different circuits. If you then surround this waveguide mesh by what we call high performance blocks, elements, or input-output ports, then you have the analogous of a field programmable gate array. So if we compare the evolution of programmable electronics and programmable photonics, we see that roughly the evolution is in a way similar with some difference in between the periods of the main events happening. But we see that we have had now already like 50 years in the first integrated optic discrete elements were proposed until these field programmable gate arrays have been proposed in the market. Okay, right. So let's go a little bit now into the FPGA device. What is a field programmable gate array? As I said before, it is a photonic core made of this programmable waveguide mesh, which is surrounded by high performance photonic blocks, which are a kind of application specific and photonic circuits. But in order to operate this device, we need an electronic tire, which is in charge of controlling the photonic elements and programming them and providing the electronic signals that are required to program these elements. And on top of that, we have a software tire that is in charge of control of providing the software to program, to optimize, to configure, and operate the whole system. So the core, which is the core of the FPGA, is a 2D mesh of interconnected reversible unitary gates, and each one is implementing a unitary analog 2x2 transformation. And we connect them in a kind of 2D array as it is shown here. So as a difference with electronic FPGAs, these are not irreversible 2x1, but reversible 2x2 transformation gates. And you can implement this, as I said before, either with a tunable directional coupler, followed by phase shifters, or by a tunable 3 dB Mach-Zehnder interferometer, followed by, as well, by phase shifters. This provides you with the possibility of managing the power transfer between any input-output port independently from the phase shift. So at the end of the day, you have multiple elements where you can independently configure the amplitude and the phase of the incoming signals. And as a consequence, you have like multi-port interference manager, which you can program to do as many functionalities as you want, as we'll see in the next slides. So it turns out that you can join and connect these 2x2 gates in many ways, but there are three basic ones, which I show here, that give rise to three different topologies: the square, the triangular, and the hexagonal. And I'm going to show you some hardware configurations of simple waveguide meshes that have been demonstrated so far. This corresponds to a silicon nitride square array. This is a silicon on-insulator hexagonal waveguide mesh. And the one that you have here is a silicon nitride triangular waveguide mesh arrangement, as you see here. So in addition to that, we have that, as we have seen before, that we can surround the waveguide mesh with specific circuits, which are called high-performance blocks, and it can be many kind of different elements, from reconfigurable delay lines to high-performance filters, AWG devices, sources, modulators, etc. And these complement the waveguide mesh. So the full optical core is composed of this waveguide mesh, and it is surrounded by these high-performance blocks. The waveguide mesh can do two main tasks. First of all, it can emulate internal circuits by programming, but they can also connect these circuits or provide connections in between these high-performance blocks. So it's a very, very versatile configuration, just like FPGAs operate in electronics. There is, however, one difference, that while FPGAs in electronics work on digital electronic signals, FPPGAs in optics work over analog lightweight signals. So instead of working with zeros and ones, we work with amplitudes and phases. In addition, the electronic tire, as I mentioned before, is a hardware that is electronic hardware that is required to monitor the FPGA status. So it is basically composed of three elements. We need one part to sense the status of the FPGA elements. So we know what is the status, whether they are drifting or not. And we get this part of the system that monitors this FPGA status, provides information to a processing unit that will actually correct the settings of the elements if they are deviating from the targeted values, or providing driving signals if we want to change the programming of the elements. So we need this monitoring array, we need a processing unit, and we need a driving array. All this is the electronic part that surrounds the optical core. We also need, as I said before, a FPGA software layer. It is composed by two main layers, sublayers. A low-level layer that is composed by basic routines that are used to drive actuators or extract readouts from on-chip elements. And then we have a high-level layer that is in charge of providing the programming software, which can be based either on global algorithms and presets, which require a pre-characterization of the FPGA core elements, or we can use computational optimization algorithms, which require no knowledge of the status of the FPGA. This software actually will run on its own and will program the device to match our specs. And moreover, it will also track changes to correct deviations, or even if, for example, given the event that some part of FPGA is not working correctly, it will try to recover or heal the FPGA device, or reconfigure it in a way that it still provides the service, although it uses another elements in the circuit footprint. So we see our FPGAs in all these, as I said before, a set of emerging applications that range from communications, self-driving, data center interconnections, 5G, etc. But also, moreover, as well, in, as I said before, applications that will need other computing paradigms to work. And in these, we include, for example, quantum computing, neurophotonics, frontier research in physics, emulation of complex physics mechanisms, etc. So to make FPGAs viable, we need to solve several scalability challenges. Some of them are physical, that means hardware, and we have to overcome limitations that stem from power consumption, from the need to monitor hundreds or thousands of variables, the need to overcome crosstalk from adjacent optical signals, even from thermal effects. And we also need to overcome software scalability challenges. So we need to have faster configuration times. As I said before, we will need to manage hundreds and thousands of variables, and we need to have or devise robust solutions in order to manage the operation of non-ideal components. And all this has to be framed into a single element. So, as a summary and conclusions of this short talk, I hope to have convinced you that programmable photonics is going to happen, yes or yes. It may not be our conception of FPGA, but it is going to happen. And that it shares commonalities with integrated electronics, yet it is completely different in a way because it's analog instead of being digital. But in particular, in this talk, I have focused on the field programmable gate, photonic gate array. I have introduced the hardware and software of the types of the structures, and I have provided some experimental or some experimental examples and applications. And I have also addressed some of the future challenges that will have to be addressed if we want to make this device something that goes into the market. And this basically comes from overcoming actually scalability limits, both in hardware and software. So thank you very much for your attention. It's been a pleasure. And I look forward to have the chance of talking a little bit more about this exciting area in future talks.